In this video, we continue to talk about basic definitions of rings and introduce the definition of a field. So a commutative ring is a ring where multiplication is commutative. And most rings that I've dealt with are commutative rings. In fact, for example, the integers, the polynomial rings, they're all commutative. One important ring, though, that is not commutative is the ring of n by n matrices. Now, just as a reminder, the 1 in this ring of n by n matrices is the identity matrix that has 1s along the diagonals. And now let's introduce another term, the unit. So a unit of a ring is an element that has a multiplicative inverse. In other words, there's some other element in the ring so that when you multiply those two elements, you get 1. So units in the integers are 1 and minus 1. Why isn't something like 2 a unit? Because the multiplicative inverse of 2 would be 1/2, and that's not an integer. It is a fraction though, and so the units in the rational numbers are everything except 0. For example, if you have a fraction 3/5, its multiplicative inverse is 5/3 because 3/5 and 5/3 multiply to 1, and so everything except for 0 has a multiplicative inverse. This will be an example of a field where you can divide by everything except 0. Okay, then the units in the ring of matrices are the invertible matrices. That's the general linear group. A division ring is a ring where all non-zero elements are units. In other words, you can divide by any non-zero element, so that's why it's called a division ring. And a field is something similar. It's just where you have a division ring that's also commutative. The multiplication is commutative. And so examples of fields are the rational numbers, the real numbers, the complex numbers, and there's other examples as well. But the main idea of a field is you can add, subtract, multiply, and divide by non-zero elements. Now, given two rings R1 and R2, the direct product is a new ring, and it's denoted R1 cross R2. Even though we use times, this is not multiplication of numbers. We've seen this in the context of groups, that it's the set of ordered pairs, R1 and R2, and addition and multiplication are given component-wise. So entirely analogous to the setting of groups. As an example, the product ring Z5 cross Z12, if I take two elements 2, 3, and I want to add that, if I take one element whose components are 2, 3, and another element whose components are 4, 5, if I add that, I add the components component-wise, so 6 and 8, and 6, 8, well that's 6 is the same as 1 in mod 5 land, so I get 1, 8. Similarly, 2, 3 times 4, 5 is 8, 15, which is 3, 3, since this 15 is taken mod 12. The multiplicative identity is 1, 1, and the additive identity, or the 0, is the element 0, 0. Now, a proposition, which I don't think I'll prove, but is the following. Units in Zn are the numbers that are relatively prime to n. This can follow from the Euclidean algorithm, actually. But anyway, let's do an example first. That Z12, as a set, is 0, 1, 2, 3, all the way up to 11. And it's a ring because it's got addition and multiplication. And the units are 1, 5, 7, and 11. These are exactly the numbers we were denoting Z12 with an asterisk, or Z12 star. And these are the numbers that are the units because they have multiplicative inverses. You might say, well, isn't the multiplicative inverse 5 1/5, and 1/5 isn't in here? Well, sort of. 1/5, what does 1/5 mean? In some sense, it's a number x, so that 5 times x equals 1. But we want this to equal 1 in this ring, where 1 is actually 1 mod 12. And so there is such an x that in this set here, that such that 5 times x is equal to 1 mod 12, you can just naively go through the elements and check, and you'll see that 5 is its own multiplicative inverse. Namely, 5 times 5 is 25, which is 1 more than 24, and 24 is a multiple of 12. So 5 does have a multiplicative inverse in this ring. It does not have a multiplicative inverse in the ring of integers, but in the integers mod 12, 5 does have a multiplicative inverse. So now Z12 is not a field because 2 doesn't have a multiplicative inverse. You might say, well, why not? Well, 2 times x equals 1 mod 12. That has no solution because 2 times x will always be an even number, and any number that's 1 more than 12 will be an odd number. Okay, so Z12 is not a field. But on the other hand, if you have a prime number, p, Zp is a field. In other words, well, we know it's a ring. That's okay, but then why is it a field? Again, what's the difference between a ring and a field? In a field, you can divide by non-zero elements. So, in other words, well, more precisely, you have multiplicative inverses is a more technical way of saying divide. But, okay, how can we divide by a number a, or what's a multiplicative inverse of an a? Well, by Fermat's little theorem, we know that a to the p minus 1 is congruent to 1 mod p for any a that does not divide p. So remember, Zp star, that's all the numbers in Zp except for 0. And multiplicative inverse of a is a to the p minus 2. Again, this is the multiplicative inverse of a in the ring Zp. And why is this a multiplicative inverse? Well, because if you take a and multiply by a to the p minus 2, you get a to the p minus 1, which is 1 in mod p land. And so that's why a has a multiplicative inverse, as long as it's not 0. And so that's why Zp is a field. And it's a field with finitely many elements. And such fields, there are many of them, have applications to coding theory and cryptography. But we won't get into that. But I did want to just mention that there are practical applications of knowing Zp is a finite field. Okay, let's move on to some more terminology associated with rings. So an integral domain, or sometimes just domain, is a commutative ring with unity. So almost all my rings have unity, so that's something that Fraley just throws in to make sure. Okay, such that if a times b is equal to 0, then a equals 0 or b equals 0. And you might wonder, well, if a times b is equal to 0, doesn't one of them have to be 0? And the answer is no. So for example, in Z4 or Z6 or Zn for any n that's not a prime, these are not integral domains because 2 times 3 equals 0 in Z6, because 2 times 3 equals 6, and 6 is the same as 0 in mod 6 land. But 2 and 3 are not 0. So here's how a situation where you have two things multiplying to 0, but neither one of them are 0. And the 2 and 3 then are examples of what's called zero divisors, namely non-zero elements, so that there's some other element so that the a times b multiplies to 0, even though a and b are not 0. So again, this is what can happen in something that's not an integral domain. So some examples of integral domains are the integers, because if you multiply two integers and they happen to multiply to 0, one of them has to be 0. So that's a familiar fact from elementary school. Z mod p for any prime p, and then any field, and then also the ring of polynomials with coefficients in any field f. So here's a proposition, is that in any ring R with no zero divisors, in other words, if R is an integral domain, the cancellation law holds that if a times b equals a times c, and a is non-zero, then we can sort of quote-unquote divide by a, and we can conclude that b equals c. And the proof is simple. So we start off with ab equals ac, subtract off the ac from both sides to get this, factor out the a, and so now we have two numbers, or two elements I should say, that multiply to 0, and we're assuming that a is non-zero. So because we're in a domain, that means when you have two elements that multiply to 0, one of them, at least one of them, has to be 0. And we know, so one of A or B minus C has to be 0, but we know that A is not 0. That's part of the hypothesis. And so that forces us to conclude that B minus C equals 0. Since R is an integral domain, or another way of saying it, has no 0 divisors. In other words, two elements can't multiply to 0 without one of them being 0. Okay, so then we get B minus C equals 0, so therefore B equals C. Another fairly simple proposition is that every integral domain with finitely many elements is a field. So, okay, so for the proof, we need to show, what's the crucial fact about a field? Well, that every non-zero element has a multiplicative inverse. So let our ring be, A1 up through AN. It has finitely many elements, so we stop at some number n. And let A be an element of the ring that's non-zero. We want to show that A has a multiplicative inverse. And here's the trick, is to consider the set A times R, which is just taking the ring R and multiplying every single element by A. And what the cancellation law that we just proved says that all these elements are different or distinct, because if two of them were the same, say A times A1 equals A times A3, then we could cancel the A's and just get A1 equals A3. Okay, so since this is a list of n elements, and R has n elements, and so the number 1 must be one of these. So the subset actually could be, it's true, but it's also stronger that it could be equals. I could have written equals here. Okay, and so A times A1, AI, for some I, one of these, is equal to 1, and so that shows that A is a unit. So this is a fairly tricky proof. Not the most important proposition, but interesting nonetheless.